In this example, I'm going to factorize this quartic polynomial, and I'm going to do it with a couple of my new methods. Now, I could do this by just using the factor theorem, trial and error. I could put this formula into my calculator and use trial and error to try and find some of the zeros. Sometimes I might be able to use that method to find all of them, but after a while it might get tricky and I might give up. I might resort to long division to find the rest. But now I've got a new method that I can resort to if I get into that situation. So I've put this into my calculator and I've done some experimenting, and finding p of 1 is equal to 0 was helpful. I've also found that p of -4 was equal to 0. So what does that tell me? Well, it tells me that I've got a couple of my factors worked out. I can see that p of x must be able to be written with, well, the a out the front is just 1, so I can leave that. And if I found one of my zeros was 1, then one factor will be x minus 1, and another factor will be x plus 4. Okay, so remember not to mix those up. If your 0 is 1, your factor is x minus 1. And if your 0 is -4, your factor is x plus 4. Because, of course, the zeros are just those numbers that you can sub in here to make any one of those sections 0. So I'm imagining now that if I've got a quartic curve, then I'm sort of looking for two more sets of brackets. And yet, with this number here being 1 and this number being -4, I'm feeling a bit stuck because I've already got my lasts as -4. And I'm curious about what's going to go here. So at this point, I could multiply these two together and say I've got x squared, what's that, plus 3x minus 4. I could divide the entire polynomial, putting it down there, to find what's left over. And that's what we were sort of resorting to in the last exercise. But instead, I'm going to use my knowledge of the sum and the products of the zeros. So if I've already found two of the zeros, let's say we can let alpha equal 1 and beta equal -4, then the other zeros will be gamma and delta. So if I know that alpha times beta times gamma times delta is equal to, now it's a quartic curve, this is the product of the roots, so it's E on A, and if I write that down every time it helps me, and E is -4, A is 1, so this actually equals -4, then subbing what I know, I've got 1 times -4, that's -4, and then I've got the two roots that I don't know yet, and all of that has to equal -4. Dividing both sides by -4, I can see that the two roots that I don't know, when they're multiplied together, need to equal 1. Now, quick confirmation by using my sum of zeros, I know that alpha plus beta plus gamma plus delta is going to equal -b over a. And subbing in what I know, if I have 1 plus -4, that's -3, plus my other two roots that I don't know yet, that's going to equal -b on a, and b is 1. So this is going to be -1. Now, adding 3 to both sides, I can see that gamma plus delta needs to equal 2. So these are the equations I need to solve simultaneously. I think you'll agree this is a very easy simultaneous equation to solve. I need two numbers that add up to 2 and multiply together to make 1. Clearly, they're both 1. And so this tells me that my other factors must be x minus 1, and in fact, 1 would be a triple 0. So I can then write it a little bit more neatly because I've got 3 of those zeros that are the exact same. It's going to look like that. I can then, of course, use my graphing skills to graph this nice and easily. I can see that it's got zeros at 1 and at -4, and this is a normal 0, so the curve's going to pass through this point, whereas it's going to go through this one with a wobble because it's a cubic 0. I can see also it's a quartic curve and it's an upright one, so it's going to start high. It's going to go through this intercept, but it's going to go through this one with a horizontal point of inflection, which at this stage of the course we're treating just as a wobbly intercept.